Alrighty, last video on Euler's method. We're going to go ahead and walk through at least one, hopefully both of the AP questions that I've pulled out. Okay, let's go ahead and look at this one. And let's see if I can zoom in just a smidge. And let's go ahead and see what they're asking here. Now, consider the differential equation dy dx is equal to 2y minus 4x. The slope field for the given differential equation is provided, and of course on the actual question it was. Sketch the solution curve that passes through the point 0, 1, and sketch the solution curve that passes through the point 0, negative 1. Well, we've done a little bit of that, so we're not going to deal with that right now. I'm more interested in part B. Let f be the function that satisfies the given differential equation with the initial condition. There it is, okay? So we already have the slope generator, okay, the differential equation. I want the initial condition 0, 1. Use Euler's method starting at x is equal to 0, that's easy enough, with a step size, there's my delta x, to approximate, okay, so I have all four pieces of information. Show the work that leads to your answer, okay? Well, let's go ahead and there we go. That way we don't waste paper. Okay, so I know that step 1, okay, I'm given 0, 1, okay, and I know that y prime of 0, 1 is going to be 2 times y minus 4 times x, or just 2. I have point, I have slope, I can go ahead and keep going from there. So y minus y1 is equal to m times x minus x1, or y is equal to 2x plus 1. That is my first line that I'm going to use to approximate. Now I need to evaluate that at point 1, or 1/10. You know me, I like fractions, so we're going to go with fractions on this one. So y1 at 1/10 is going to be 2 times 1/10 plus 1, or that's 1/5 plus 1, or 6/5. So I know that my ordered pair is 1/10, 6/5. Notice that I have already started on step 2. I have my ordered pair. Now I need y prime of 1/10 and 6/5. That's going to be 2y minus 4x. Okay? That winds up being 12/5 minus 2/5, or 10/5, or 2. Well, that's kind of neat. Let's make sure that I did that correctly. So that's 2y minus 4x. Yeah, I think I did that correctly. Okay, so now I know that what I have here, okay, is y minus, let's see, I have my point, I have my slope, y minus 6/5 is equal to, sort of pull that back a little bit so I can see a little bit more of the paper, 2x minus 1/10. So y minus 6/5 is equal to 2x minus 1/5. We'll go ahead and add 6/5 to both sides. That winds up being y is equal to 2x plus 1. Okay, so let's go ahead, and that is y2. I'm going to evaluate it at 1/5, right? 2/10 at 0.2. And then I need 2 times 1/5 plus 1, and that's going to wind up being 2/5 plus 1, or 7/5. Okay? Now, what I have here, okay, is actually the answer that is given. Okay? So I have taken 2 steps. Now it was a little bit weird, obviously, to have y1 and y2 be the same. And that has everything to do with the particular solution that is going on here. And I'm going to go ahead and show it to you. Okay? This right here, notice that this is the slope field. Notice that one of the solutions that runs right here that goes through 0, 1 just happens to lie on the very line that actually winds up being linear. So basically if you're going to be doing Euler's method, your trajectory is going to be right along a linear function. And that linear function, of course, is going to be 2x plus 1. And that is why both of these wound up being 2x plus 1. It wasn't some huge coincidence. It was the fact that that particular solution for the differential equation happened to be linear. Okay? Now we don't actually have to move on and do any other pieces of this particular one. What I would like to do now is I'd like to move on to the one from 2005, which also has an Euler's method component to it. Okay. Alrighty, this is from 2005, question 4. It says, consider the differential equation 2x minus y. Okay. Now, notice that on this one, it's not provided for you. They're actually asking you to sketch it. And notice that there aren't really that many points, okay? And you would just go ahead and sketch it for the 12 points that are provided, making sure that you do an accurate job, right? Now, let's look at part B. It says, the solution curve that passes through the point 0, 1 has a local minimum at x is equal to natural log 3/2. What is the y-coordinate of this local minimum? We're not going to be dealing with that right now. We want to deal with part C, which has to deal with Euler's method, okay? Since that happens to be what we're doing right now. So let y is equal to f of x be the particular solution to the given differential equation. Now remember, I need 4 things. I need the differential equation. Got it. Initial condition. Got it. I need, of course, we're starting at x is equal to 0 at that initial condition. 2 steps of equal size, that's going to tell me my delta x, and I'm going to be going to f of negative 2/5. Okay. Now notice that I'm actually taking a trajectory to the left, okay, instead of to the right. It doesn't really matter. Negatives obviously increase the likelihood of careless errors, but the arithmetic for a calculus student shouldn't be too tough, okay? So let's go ahead, and I'm going to go ahead and just rewrite the information on this sheet so we don't have to keep the AP question in front of us. I know that y prime is 2x minus y. I know my initial condition is f of 0 is equal to 1. I'm looking for f of negative 0.4, and my delta x is negative 0.2. Okay? Now obviously I like fractions, okay? I think fractions are easier to deal with, so really I'm looking for f of negative 2/5, and delta x is negative 1/5. Well, let's go ahead and do step 1. Step 1, I need point and slope. Now I already have my point, it's 0, 1. I now need to assess or evaluate y prime at that point. So I have 2x minus y, or negative 1. Point, slope. So y minus y1 is equal to m times x minus x1. And that winds up being y is equal to negative x plus 1. That is my first trajectory. That's my first tangent line, okay? I now need to evaluate that at the first step, okay? So I'm going from 0 back to negative 1/5. So I need to evaluate y1 at negative 1/5. That's negative 1/5 plus 1. That winds up being 6/5. So that gives me an ordered pair of -1/5, 6/5, and I know that y prime at that needs to be the slope for this new line, the second step in Euler's method. So I know it's going to be 2x minus y, that's -2/5 minus 6/5, or -8/5, point slope. Y minus 6/5 is equal to -8/5, okay, x plus 1/5, or y is equal to -8/5 x minus 8/25 plus 30/25, right, which is the 6/5 added to the other side. This is obviously going to be 22/5, positive 22/25, sorry, 22/25, and that, of course, is y2. Now, all I have to do is I have to evaluate y2 at -2/5, and so I get -8/5 times -2/5 plus 22/25. That's going to be positive 16/25 plus 22. So it's going to be 38/25. That is your approximation for this particular problem. Okay? Now, they actually give us the answer of 1.52 because they're a bunch of decimal people, and I just can't fathom that, but of course we all know that I'm old school. But just in case you were wondering, 38/25 is indeed 1.52, okay? Now notice that in their solutions, they've actually done it more formulaically, okay? If I'm going to be doing this, I want to see the equations, okay? And here's the thing, if you do it formulaically, remember, first of all, formulas can be forgotten. And second of all, formulas oftentimes stand as a substitute for conceptual understanding. If I'm just going to do two or three steps, I'm not going to use a method. I'm going to go ahead and actually get the equations of the line because that's actually what's going on. If you want to go ahead and use this method, and it's in your book and your teacher's probably going to teach it to you that way, that's fine. I'm more interested in the conceptual understanding, and therefore I've always taught it using the actual equations of the lines that are giving it to you, okay? Now, I've told you that you can drop it into an Excel spreadsheet, and obviously the Excel spreadsheet is an expression of that formula. I'm not going to get into that. If you really have a question about that, I guess you can shoot me an email, and if I have time, I'll try to get it up. Obviously, you're not going to be tested on your use of Excel spreadsheets to help you solve Euler's method problems. But it is actually kind of neat, and I wish that I actually had the time and the wherewithal to do it right now. I do, however, have to get onto videos for the next couple of sections so that you can do well in your test, and so it's always a matter of what to include and what to exclude. If you have any other questions, please do email me, and I will, of course, get back to you on those. Look forward to seeing you at the Skype session, guys. Bye.